Okay, so we are talking about stress. Statically admissible stress field. So, statically admissible stress field should satisfy some condition. So, first one, T. So, inside of the body or out the surface of the body, this condition should be satisfied. Divergence and low F equal 0. So let me see. Low F F minus gamma low gamma equal 0. And stress should be symmetric. In the body, these three conditions should be satisfied, and on the surface, D is externally applied surface force on surface. So all of these are equilibrium equations. Okay, so equilibrium equation, local equilibrium equation in the body. This is equilibrium equation too, right? This is equilibrium on surface. So stress field should satisfy all of these equations. And let me note the another condition for displacement is this one. U equal UD on surface UD. So displacement field also should satisfy its displacement boundary. So here UD is prescribed displacement. We are saying this is a kinematically admissible displacement field. So we are using the word kinematic for displacement and motion, but we are using static for the stress and force. So in solid mechanics we have a body, right? And some force is applied. This is a prescribed force or surface force. And we have some boundary condition. This part can be fixed. So this area is displacement boundary, and this area is a force boundary, TD. So whole boundary equal sum of force boundary plus sum of the displacement boundary. So So we need to have this concept. This is a very typical structural problem, also solid mechanics problem. We have body, and it is subjected to some force, and it has some displacement boundary condition. So, in general, we have two boundary conditions in static analysis: force boundary and displacement boundary, right? But for dynamic analysis, we can have a velocity boundary or acceleration boundary. So we are saying something like an initial condition, right? Because we have in static analysis, the main variable is force and displacement. But in dynamic, we need to consider velocity and acceleration too, right? So, okay. I think you understand. Okay, so now let me give you an example. So I introduced a lot of equations, right? Equilibrium equation, usually action, reaction, no. Example. This example will give you a further understanding. Two layer soil problem. Let's say this is x-axis, or let's say just EX. And this is a surface of the soil. And we have a two layer of soil. Here, soil layer 1, soil 1. Here, soil 2. Okay, this is surface. So you are here. Okay. And this is y-axis. Sorry, this is not y. This is a y-axis. EY. And y equal 0, y equal minus h. And on the surface of soil, the uniform pressure P is applied. P. You can think that P would be the air pressure, okay? Or you put some mass on the surface of the soil, okay? Then that mass can give some uniform pressure. So what I wanted to find is that the stress field here, stress field 1, stress field 2. So I wanted to find the stress field in soil layer 1, soil layer 2. Okay? And this is the infinite domain in x direction and g direction. So size of this problem is very big. Okay, so x direction in y direction, infinite. So problem becomes simple. Okay, then let's find the stress field. This is what we want. You know about the stress field, right? It has 9 components. Stress, XX, stress, XY, stress, XG, YY, YG, GG. But this is symmetric. So we need to find 6 components with that kind of equation. Okay? Actually, I need to say here, let's find statically admissible okay. First, at y equals 0. So at y equals 0 is this here. This is a boundary, right? Where we should consider boundary condition. At this boundary, what's the surface vector normal to the surface? N. This is n, right? N. That surface normal vector n equal EY, right? Then stress 1, soil layer 1, okay, and equal, what's the T? Externally applied fraction. Its magnitude is P. What's the direction? Minus EY, right? Minus EY, right? So, minus P EY. This is the equilibrium equation on surface, right? Then, let's put the this matrix into that equation. Then, here n equal 0, 1, 0, right? Because this is a base vector for E1. So this is a 1, 0, 0, 1, 0. 0, 1, 0. So stress 1 here 0, 1, 0 equal minus, so okay, 0 minus P 0, right? So here stress XX, XY 1, XG, something like that. YY, yg gg. So if you multiply this matrix and this vector, you are going to have only this component, right? So for the all of these equations, we have a stress yy, xy, stress xy over soil layer 1 equal 0, right? And stress yy 1 equal minus p, stress gy 1 equal 0 at y equal 0, right? At y equal 0. At y equal, but for other position, we cannot say stress yy is minus p and xy is 0, right? So this is only the condition when y equals 0. So this is that comes from the equilibrium equation on surface. Okay? Then now how about the equilibrium at y equal minus h? There should be some continuity in the stress field, right? Because the soil layer 1 and soil layer 2, they are facing to each other, right? So we need to apply action reaction law. Second, y equal at y equal minus h. Y equal minus h. Let's consider the soil layer 1. This is our body. For the soil layer 1, the surface normal vector is this one, right? Let's say this is a n1, right? How about soil layer 2? This is normal direction for soil layer 2. Let's say n2. So n1 equal minus ey, n2 equal ey, right? So at that line, y equal minus h, equilibrium should be specified. That is T traction actually T1 E T minus E1y plus T2 EY equal 0, right? So here, this will be a T1. This is a T1 is a traction of soil about the soil layer 1. T2 is a traction of soil layer 2. Okay, this is a N1, N2. So, what happened in this equation? So, this equation means stress 1, okay, multiply E, Y, actually minus, plus stress 2, E, Y equal 0, right? So, stress 1 EY equal stress 2 EY. So, if we multiply EY to the stress tensor, we can pick up only this component, right? So from this equation, finally we have stress xy 1 equal stress xy 2 yy 1 equal yy 2 gy 1 equal gy 2 at y equal minus h. So this condition give us a meaning of continuity of stress, right? On the surface and then on the interface. Okay, actually this is surface is also interface too. So interface. Understand? Any question? So you need to understand step by step, right? That's physical problem. So to solve some physical problem, I'm applying the equation we derived before. So now let me talk about local equilibrium equation. 3 local. So we have 3 local equilibrium equation. I'm going to write down xx xy xg plus fx minus rho gamma x equals 0. This is first equation. Second, yx yy yg plus f y minus rho gamma y equal 0. So now we need to use this looks complicated equation, right? This looks complicated. Okay, let's think about this problem. Okay. So we have an infinite in x direction and y direction. So something like this. We have a very, very, very infinite area of the plate here. Okay? And uniform pressure is applied. Right? So now, so stress field will change in x direction, right? Do you think stress field will be a function of x? Just think. How about the stress can be function of g, function of y? Actually, for this kind of problem, all the stress or displacement field will be only function of y. This is just one-dimensional problem like a bar, right? So, stress field will be function of only y. So, actually, you need to get this concept okay, from your engineering sense. Okay, so stress will be only function of y. Then we don't need to consider this term, right? And also, this is a static problem or dynamic problem? Static problem, right? Right? So we don't need to consider this dynamic term, acceleration, right? And now let's think about the body force. Okay, what kind of body force is applied here? F. What's the F? Here, gravity, right? G. G will be applied. Gravity load, G. So, let's say the soil layer 1 has a density rho 1, rho 1, density rho 2. So for soil layer 1, F, let's say F is a body force become 0 minus, so okay, let's, F will be minus rho 1g EY, right? Let's say F1 is a body force applied in soil layer 1. How about soil layer 2? F2 equal minus rho 2g EY, right? So this equation become y xy equal 0. This is 0. This is 0 too, right? Gravity load is applied in only y direction. And how about this one? Y okay, minus, so rho g equal 0. So here rho can be a rho 1, rho can be rho 2. So we need to, so let's say like this. Okay. Okay, this is okay. Partial y, g, y equal 0. So now we have only simple equation. Then what's the next? Huh? This is all the differential equation. For example, I wanted to find xy, stress xy. How can I do that? We need to integrate, right? So let's integrate. Take the integration. So stress xy will be some constant, let's say cxy, and stress yy equal rho gy plus some constant yy. Okay, and stress gy equals some constant gy, right? Right? Then force. Okay. Now what we need to do is to find that constant, right? How can I find that constant? We need to apply the boundary condition. So for example, soil layer 1. Soil 1. Okay. Soil 1, we can use xy equal 0, yy equal minus p, gy equal 0 at y equal 0. Let's use this equation. soil layer 1. Then, for the soil layer 1, we can have a stress field xy 1 equal 0. Stress y 1 equal, let's put y equal 0 here. Then Cyy should be minus p rho 1 gy minus p. Stress gy equal 0 to 1. So now we find the 3 stress component for soil layer 1. Okay, and soil 2. To calculate the stress component of soil 2, we need to use this condition. xy 1 equal xy 2. yy1 equal yy2. gy1 gy2. Right? At y equal minus h. Right? So, let's consider the first one here. Stress xy1 is this one, is 0, right? 0 equal, here, xy2. xy2 equal, over there, c xy2. So, for the constant cxy for soil layer 2 is 0. So we will have a stress xy2 is 0. Right? How about the second equation? Second equation here, this one. Let's put the y equal minus h. Rho 1 g and minus h minus p equal rho 2 g minus h plus cyy2. Okay, so yeah, you need to consider this equation. So we can find cyy2 here. So stress yy2 equal rho dy okay, minus p minus rho 1 g h plus rho 2 g h. here we should be rho 2. And similarly for stress to gy equals 0. So now we find 3 stress components for soil layer 2. Something like this. Understand? Little complicated. So finally, let's summarize the final results. So, for soil layer 1, 6. Soil layer 1, stress 1 equal, we find only 3 components. Stress xy 1, stress yy 1, stress gy1, right? We don't know these components, right? We don't know yet. And here with stress xy 1 equals stress gy 1 equals 0, stress yy 1 equal rho 1 gy minus p. And stress 2, stress field of soil layer 2 equal similar xy 2 yy 2 gy 2. So we don't know yet. With equal 0 and gg2 equal rho 2 gy rho 2 gy plus h minus rho 1 g h minus p, right? Okay, so until now we find only 3 stress components, and actually stress is symmetric, right? So we need to use symmetry of stress. So here we also know stress yx1, right? And stress yg1. Here stress yx2, stress gy2. But we don't know this one. We cannot calculate the information we have here. To find that kind of thing, we need to use the Moore equation. So this is the final answer. Stress, the statically admissible stress for the two-layer soil layer problem. Now let me ask you a question. We consider soil layer, right? Soil is a solid, right? Then how about this is not soil layer, for example, fluid layer. Oil 1, oil 2. And there is some air pressure, P. Then what happened? What's different? What's different? So fluid have a same pressure in all the direction. So it means stress XX, YY, GG are all the same. So if I consider so oil layer problem or just with a different density, we will have this component too. And this is same to the Y. So we can have all the stress field. Right? Okay, so any question?